Hey everyone, welcome to another session of CeerazzleDazzlePhysics. In today's session, we're going to be talking about capacitor graphs for charging and discharging. So in today's lesson, we're going to be talking about capacitor graphs when we're charging it and when we're discharging it. Alright, let's get straight into it with the following scenario. So here guys, I have my capacitor, and we've attached it to a power supply. And there's a switch in the circuit. And we're going to be looking at when the switch is pressed, what's going to happen to the voltage against time, the charge against time, and the current against time. So what's going to happen for this actual capacitor? And when I mean the voltage around the capacitor over here. The charge, I'm going to talk about the charge stored on the plates over here. And the current is going to be obviously the current that's going to flow through our circuit as well. Right, okay, so first of all, we're going to do it quite slowly. Let's say we place, let's just be honest, let's put 10 volts going in. 10 volts going in, and obviously if the circuit's open, nothing's going to happen. And the voltage across the capacitor is 0 volts at the start. Why? It's not charged yet. Obviously, there's none of the charge has been able to wind itself onto the capacitor itself. So obviously, when we click the switch, guys, what's going to happen? When we click the switch, we notice that the voltage across the capacitor will go up. So the voltage will go up. So initially, right now, it starts off as 1 volt. Then it keeps on going all the way up to what value would it be? It will reach 10 volts because obviously 10 volts coming into the circuit and obviously 10 volts coming out. So therefore, it must match up over here. So 10 volts coming in, 10 volts coming out. So initially the voltage was low across the capacitor because it was 0 at the start, and it will go up and reach a maximum value. So the voltage will go up like this. This is the kind of graph we get for voltage against time when we're charging the capacitor. Right, what about in terms of charge? So let's go back and let's open up the circuit once again. So initially, there is 0 coulombs around here. There's 0 coulombs. When you hit the switch, what's going to happen? Obviously, the charge will build up. So the charge starts off at 0 at the start, but eventually it will build up. Infinitely? Will the charge build up infinitely? Well, no. Eventually, let's just build up a bit. So let's just say, for example, we make it 10 volts here. This is positive. This terminal becomes positive. This bottom terminal is negative. This other terminal becomes negative. Okay? But as time goes on, eventually there'll be a maximum amount of charge that can be built up on here. So this will reach a maximum amount here. And this one will also reach a maximum amount. And also, if you think about it, if you're an electron and you're trying to go onto this terminal over here, you're the electron, you're trying to move on to this terminal, it's going to become harder and harder because you're bringing a negative charge to the other negative charges. Because this is really negative right now, you're trying to bring this electron onto it over here, it's going to be quite difficult. So that's the reason why eventually there's a maximum amount of charge that you can store on this plate here. So as time goes on, the charge will also go up and reach a maximum value here. Okay, so charge against time looks like the one of voltage against time. That should also make sense because we know that capacitance is equal to Q over V, and if the capacitance is constant, and therefore voltage is proportional to the charge over here. Voltage is proportional to the charge. That makes sense. That's the reason why the graphs are the same. Okay, what about current against time now? What about the current against time? So let's just look at the current. If you've forgotten what current is, guys, current is equal to the rate of flow of charge. The rate of flow of charge. So initially when the switch is open, nothing's going to flow around. But the second you close it right now, what's going to happen is the electrons on this part of the wire, obviously, there's loads of electrons initially on this part of the wire, they're going to be repelled by this negative terminal and end up moving onto it over here. So initially they move quite fast at the start. And by symmetry, the electrons on this side are going to be moving over here, leaving this terminal positive. But as time goes on, what's going to happen to the rate at which that charge is flowing? So what's going to happen to the rate of flow of charge? Is it going to be flow faster or slower? Is it going to be faster or slower? Well, hopefully we can see that the more charged this terminal becomes, it's going to be harder to put another electron onto it. It's going to be harder. So obviously it's going to slow down. So at the start it's easy to build up the charge, but then you're trying to put more electrons onto that negative terminal, but now look, it's much slower. So the current gets lower once you've actually hit the switch. Initially the current is high to whiz around to charge it, but then as it becomes charged, it becomes harder and harder to put other charges onto it, therefore the current drops down. So the rate of flow of charge goes down over here. Make sure we understand that because that's quite hard to get our head around. Right, so obviously at the start, the rate of flow of charge is going to be quite high, but as time goes on, it becomes harder and harder to put electrons on there. So obviously the rate at which charge is flowing is getting lower and lower. So that's the reason why the current one is dropping down. So make sure we know that the voltage graph goes up, the charge graph goes up, the current graph is going down for charging a capacitor. Okay, hope we got our head around that. What about now discharge of a capacitor? So what about the discharge of a capacitor? So now let's say we've charged up our capacitor and we're going to discharge it. What's going to happen to those three graphs? Alright, so what's going to happen to the voltage against time when the capacitor is discharging? So when I've hit the switch, what's going to happen is, so when I hit the switch over here, what happens is this negative charge obviously will be attracted to the positive one. So it will flow around over there. That charge will flow all the way around here to neutralize the positive charge. So initially there is a potential difference, but then obviously the second you hit the switch, that charge won't be forced to stay there. It will then flow around. So eventually the voltage will drop down to zero. So this voltage drops down to zero. Why? Because there will no longer be a potential difference between the two plates of the capacitor. So there will no longer be a potential difference between the two plates of the capacitor. So our voltage graph looks like this, guys. It starts off at high at the start, it was 10 volts, but then it drops down to 0. Wonderful. What about now the charge against time? So what about charge against time? So if we have charge against time, initially, let's just say the charge we can store, I don't know, 100 coulombs here. And let's open up our circuit once again. Obviously, it's stored here. The second you connect it, what's going to happen to the charge? So initially, the charge is quite high. The second you connect it, that charge won't stay there because this will be positive. And let's say this will be the negative version. Minus 100 coulomb there, opposite side. What's going to happen is the charge will then flow around as well. So the negative charge will leave and then travel all the way across to neutralize once again. So this will go around over here. Eventually, the charge will then drop down to 0 once again. Wonderful. So the charge graph looks the same. As time goes on, the charge graph drops down. Yeah, so guys, initially there's a lot of charge on the plates. As time goes on, the charge drops down to 0. Okay, the last graph now is going to be the current against time. So what about current against time? So let's just reset one more time. So there we go. So let's open up our circuit. Let's say at the start, initially it's charged, so therefore positive, positive, negative, negative. Initially at the start there's a high potential difference. When you hit the switch right now, we hit the switch, what's going to happen to the charge over here? Yeah, so initially what's going to happen is the charge will rush around. So the rate of flow of charge will be quite high at the start. So the current will be quite high. Don't forget, current is equal to the rate of flow of charge over here. So the current is going to be quite high at the start. But then obviously as time goes on, let's just say this becomes less and less charged. What's going to happen to these electrons? Are they going to be, is it going to be keen to rush around compared to before? So initially at the start, let's say it was loaded up. Okay guys, so as you can see, I've added loads of negative charge to the bottom and loads of positive charge to the top, just to help me explain this process. So the main thing is this. When we connect the switch, what's going to happen is these electrons, this guy is going to be so keen to move across. Why? Because it's so negative here. So it's fast to move around. Okay, so it's quite fast. The rate of flow of charge is quite high at the start. But as it starts to become less and less charge, obviously because it's losing charge, so they're going around the circuit, this electron is not going to be dying to move across now. It's not going to be dying to move across. Why? Because there's a lower potential difference. It's going to be less repelled from here, from this terminal over here, and obviously less attracted to this one over here. Still attracted, but it will happen at a slower rate. Okay, yeah, so initially when there's a high potential difference between the two plates, the charge flow is going to be quite high. Obviously because they're trying to neutralize. But as the potential difference between the two plates decreases, it's going to, what? What will it do? The rate of flow of charge will decrease. So the current will decrease as time goes on. So we end up with this graph then for the current against time. Okay with that? So now we've done 3 graphs for the discharge of a capacitor. We've also done 3 graphs for the charging of a capacitor. So look carefully at them. So let's just have a look at them both together. Okay, so here's a summary, guys. So on the left hand side, I've done all the graphs for charging. On the right hand side, I've done all the graphs for discharging. Okay, so obviously I haven't drawn them perfectly, but look, as you can see, you should be able to spot the general trends. They are all exponential functions, guys. They are all exponential functions. So look, for charging, voltage goes up, maximum level, charge goes up to a maximum level, but the current drops down. Right, so for discharging, the voltage across the capacitor will drop down as time goes on. The charge stored on the plates will drop down as time goes on. The current in the circuit as time goes on will also drop down. So don't get confused between the graphs, guys. And they're all exponential functions. We end up with the following expressions, but don't worry, I'll do another video to talk about that in much more detail. We end up with the following: V at a certain time. If I want to work out the voltage at a certain time, let's say this time over here, I simply use the equation V naught e to the minus t over RC. And we also get another equation for the charge. Charge at time t is equal to Q naught e to the minus t over RC. Current at time t is equal to I naught e to the minus t over RC. Yeah, happy with this? So don't worry about it. In the next video, I'll be talking about those equations in a bit more detail. But for now, make sure you understand where we've got those graphs and you understand in terms of physics, why are they occurring? Yes, why are they occurring? Okay, so that's it for another session of CeerazzleDazzle Physics. As you see you next time, make sure you like and subscribe to get my channel going. Have fun with the capacitors. Ciao, ciao, and goodbye.